Hello, everyone, and thank you so much for joining us today for another VES-Artex Academy webinar. Today we are joined by Dr. Mike Wolf, who is a consulting veterinarian for VES-Artex, and today he is going to be presenting on the evolution of the fresh air injection strategy in modern dairy facilities. Before we get started, just some quick housekeeping. If you have any questions throughout the presentation, please type them into the Q&A panel on your screen, and we will ask them to Dr. Wolf at the end of the presentation. So with that, Dr. Wolf, the floor is yours.
Thank you, Annie. Appreciate any of you that are joining us today, and those that may take time out of their day to watch the video later to take a look at our discussion today about injecting fresh air into the dairy facilities. So as we go on here today, that some of this, if you were watching the previous videos before the presentation, has some of the examples of what are being applied in the dairy industry. And so we're going to go explore some of these and focus more about how we get fresh air in the buildings. So again, many of you, if you've seen my webinars in the past, we had this three-legged stool of the air exchange, getting velocity to the cows, and then doing something to help cool that cow, whether it's by high pressure fog or soaking at the feed line, whatever. But today we're going to focus more on the air exchange part and how do we get fresh air into these buildings. So again, the traditional fresh air introduction is just natural ventilation. We rely on Mother Nature, depending on which way she's blowing and how long and how intense, how the barn is oriented to that airflow, the surrounding topographical elements, both natural and man-made. These are things that are incorporated into how Mother Nature works, and many facilities now add recirculating fans in that to kind of aid how Mother Nature is cooperating or interacting with the facility that the cows are in. So again, generally these barns have an inlet along the sidewalls. Some people have tried drilled holes in roofs and put cupolas on, trying to get additional inlet. There's the inclusion of baffles in these power ventilated barns. There's static pressure that's created by the fans that actually the higher atmospheric pressure is pushing that air into the barn. The fans are creating the void. And so that's how air is coming in, but it doesn't come in evenly or get distributed evenly through the barn. It's going to take the path of least resistance. Some of the challenges in more colder temperate climates is how air comes in the barn under winter conditions, that if we aren't providing enough static pressure, the air will fall into the barn instead of come in high and fast and mix with the warmer air coming off the cows and temper it. And then we end up with issues with frozen beds or alleyways at those points of entry. Again, short circuiting is always a challenge, both in their winter and summer conditions, and whether they come from the flumes, the service alleys, and connecting links to other barns or parlors that are joined to the barn. And again, the traditional tunnel barn strategy with power ventilation is limited to barns that are less than about 180 meters, around 600 feet, because of the air quality diminishes as we get closer to the exhaust fans. So these are some just pictures of short circuiting. We have a manure flume here that's pulling air up out of the manure flume area. The middle picture is actually a inlet curtain. There's some static pressure baffles or inlets above it, and the air is not coming through there fast enough to mix, and it comes in and falls on the floor. In that particular example, he was having some freeze up right here at the water crossover. And the reason it was, as you look at the picture on the right, that's where we were pulling air and humidity into this barn is in the middle of the connecting link to the parlor. And so this was confounding the air entry further up the barn, and was compounding how that air is flowing through that barn. So again, under the fresh air injection strategy, in a tunnel barn situation, in a colder climate, we're actually pushing the air in at multiple locations. So there's no one area that has more cold coming in than others. It's directed in high and fast to mix with that air that's in the barn already coming off the cows. And we are incorporating this design into barns that are up to even 300 feet wide, able to reach that air further in the barn, along with end wall fans that are appropriate for the ventilation rate that we're using. And again, we're trying to maintain that barn mostly above 32 degrees or 0 Celsius. So we don't have necessarily freeze up issues. And we're staging that to work between 4 to 16 air changes an hour when we be actively using those fans to aid through that period. And then we would start opening curtains then to supplement that. When we're doing this, because we're injecting air in at the same rate, fairly close to what the exhaust rate is, these fans are creating closer to a neutral pressure, slightly above. And so the exhaust fans do not have to work as hard to move that air through the building. And they also become more energy efficient because they're operating at a lower static pressure. And again, the curtain inlet comes on when we're maybe in the mid 40s, around 7 degrees Celsius. And then we're supplementing that way. So again, there are dairies that we're using the same strategy that runs year round. And I'll show an example later that we did a study in to kind of document that on an even longer barn than 600 feet. So this is something that's being tried on cross vent barns, is trying to inject air into these barns by using a tube system, because the challenge as these barns get wider is the air quality as we go across it. The baffles help create the airspeed that we're trying to accommodate for those cows as best we can across that area, but the air as we go further of width becomes less quality toward the exhaust side. So the strategy here is, can we inject fresh air in to help with reducing that gas buildup, get it to the cow level, and then move it out of the building. The challenge here is in that sort of a setup that in the picture shown, that's actually a 1,200 foot barn with 6 tubes that are 600 feet long. So the dynamics of how that tube is going to perform can really be a challenge in terms of the amount of airflow that you can put into it. You know, what percent of that air is actually getting brought in compared to what the exhaust rate is requiring. You know, how well do we get that fresh air down to the cows? Are we having an impact on the air quality at the cow level? And again, the advantage here is that air is getting tempered by that air coming in higher, but again, that doesn't reach the cow level. And so thoughts being, is there other ways of designing these tubes that have been used in other industrial applications that are far more aggressive in terms of the tube design for these larger facilities, as well as perhaps a fan type that may have to be looked into to actually deliver higher static, higher volume ventilation into these tubes as these cross vent barns in particular become wider. This is an example of just natural vent barns, and this is from the UK, and the strategy used here. Again, there's recirculating fans here, putting air down over the cows, and there's a measured amount to handle like the minimum couple, 3 stages of fans forcing fresh air into this building. One of the challenges in many barns in the UK is that many of the roofs are connected together. And so even though the wind blows quite aggressively outside most days, you're not truly ventilating the barn. So this is a strategy that's being used. The fellow here on the right is actually a beef barn that's been converted. It's from a dairy facility. And some of the things he's noted is better health of the animals. The bedding lasts longer because he is forcing fresh air in and getting it directed down to the animal level. Here's another example where we're using sidewall fresh air injection. Again, the idea is we push this fresh air into the building, and then it's captured by the louvered fans. In this case, it could be another type of recirculation fan, but it brings that fresh air down to the animal level. And then this is run on a year-round basis as part of the ventilation strategy. So this is some examples of what's being done to actively introduce fresh air in the buildings and not relying on the whims of Mother Nature to create that air exchange. This is a tunnel vent 8-row barn in Nebraska that the connecting link is down here in this picture to the right going to the parlor. And so if these fans are running quite actively, you're pulling air from this area down here. There's another natural vent barn on the other side, so that confounds the ability to stop short circuiting down this lane. And so during the winter months, these pressurizing fans make sure fresh air is coming into this facility here. And then come the warmer weather, the curtain opens up and these just become passive inlets for the barn for the rest of the season, because the rest of the other barns are more powered up and balance the static pressure between them. This is a what not to do. Again, any fan's got to be mounted properly to the barn structure and use recommendations by the manufacturer. In this case, just mounting this housing by the fiberglass unit here is going to cause undue stresses here. There's going to be failure here. This smaller support structure does not give stability to this fan, and this fan is at risk to both people and to itself to cause some problems. So again, it's important that these are installed properly for both animal and human safety when we are installing fans. This is a positive pressure hybrid barn that's gotten recent notice in the last few years. This is set up with the fans pushing fresh air in down the barn combined with a curtain. The ridge row is modified to accommodate the outflow so that the amount of air we're pushing in has a way to escape. And it works quite well with a 4-row barn setup. So again, those fans are 36-inch fans, 10 foot on center down the sidewall of the barn. They're providing about 2,000 CFM per cow total, which is a great target velocity or CFM to have. And again, when it's cooler weather, say below 65 degrees, the curtains open, the fans turn off, and then the barn just naturally ventilates. So again, those set points can be varied depending on the conditions. And again, as I mentioned, the ridge row's got to be large enough to accommodate the pressure that and air volume you're pushing into that facility. Otherwise, it will create just reduce performance of the pressurizing fans because of the back pressure. And again, the 4-row, when you get into a 6-row barn, that outside row is difficult to get airspeed on those cows without really moving the bedding off the beds and creating problems there. And so it's more applicable to a narrower barn or a pack barn, perhaps, that could be applied to. This is a CFD file that Mario Mondanka did an evaluation. In this barn, they're using a larger fan, a 55 instead of the 36, but then the fans are spaced further apart. So then we run into the issue of having gaps in the airflow, where some stalls have great airflow and gaps in between will have less, where the previous example where those 36-inch fans have great coverage over the whole bed area. So as we start to modify or use variations of this, the interactions between the fans and the coverage we're trying to create can be problematic. And again, that ridge row has got to be open enough. In this design that I'm showing here, there's this area up here where the opening is. When the winds are coming from this direction, this is going to help greatly with the removing the air from that, along with where you're pressurizing. But when Mother Nature comes this way, that has a confounding effect, and it's kind of working against the pressurizing you're trying to do in the barn. So these are prevalent in areas where people don't want to have rain or snow coming in onto their beds or feed alleys, but they do have the downfalls that, depending on what Mother Nature is doing, can have a huge impact on how that barn is going to perform. So this is a video again of a pressurizing fan here on the side and coming into a louvered fan that's going to deliver that air down into the bed. And this is a wintertime example of how the air is coming in slow, and but bringing a good share of that fresh air is getting put down. And this is a 1,000-foot long barn that this has been applied in. So we also have this application in parlors where we're pushing fresh air into these parlors that will be exhausted out into the holding pens. And so because this is where we're producing food, we want to make sure that the cleanest air is here where we are producing milk, and for both animal comfort and the employees. And many times, depending on the climate, the high pressure fog can be applied to those pressurizing fans to help cool that air as well. And again, the bulk of the air then is going to be expelled out into the holding area to supplement that. On the right, we have a holding pen that has recirculating fans. And again, it can be varying types of fans, or as long as they create the proper coverage. But on this right wall over here, these are pressurizing fans, again, that are pushing in fresh air, that we're going to try to be closer to that 1,000 CFM per cow plus being pushed into this barn, and at least a minute air exchange in this area, because the intensity of the heat that's coming off these cows, along with soakers. And again, high pressure fog can be added to those pressurizing fans to help cool that air along with the soaker system. So it's got a tunnel fresh air injection. The components, we got the injection fans that are down the sidewall of the barn. We have the recirculating fans that are over the cows to bring that fresh air down to the cows. We have the exhaust fans on the far end. And then we have a curtain inlet of the size that's appropriate to handle the area required for the upper stages that are not provided by the pressurizing fans. And then we got to have some automated control in order to make this whole system coordinate together as it ramps up and down, depending on the daily changes and the climate changes as we go through the year. So again, some of the issues with temperate barns, we have freeze up, that we need to get that air coming in high and fast so it mixes with the air in the barn. And again, we bring that in over multiple locations, as I was showing you in that picture of the pressurizing fans. And then the recirculating fans grab that air and bring it down to the cow level, both to help dry bedding and move gases along to the exhaust fans. And in the summertime, they're creating the extra velocity that we want over these cows. Again, if we're not moving curtains around in those transition times between, cold or not, that's when we end up with curtains getting jammed. And that's one of the biggest headaches, along with overhead doors on dairies in temperate climates, is curtain issues. So that's why in some dairies they have chosen to abandon curtains totally and have gone to a fully pressurized system of pushing in the same air that they're exhausting. And there's a number of robot setups that are using that strategy. So again, we're getting this air down to the animal level, and the dilution of this down in the cow's environment. And the whole idea is that we're ventilating cows, not barns. Excuse me. And again, by reducing the static pressure, we reduce the short circuiting, because we're lowering the amount of draw from areas that we do not necessarily want that air coming from. So when we get to summer, we still got the same short circuiting reduced because we're pushing air in. And again, as we get barns that are greater than 500 feet, that's not recommended, because of the quality of the air on those cows further downstream is not going to be good. And again, if we add it down the length of that barn and get it directed to the cows, that gives them a much higher quality environment. And again, we can actually reduce the air changes per hour. That the old thumb rule that we needed to have a 1 minute air exchange in most climates is not deemed to be necessary. And I'll show you an example here later of a barn we actually did some studies in. So again, ventilate the cows, not the barn, as your primary goal. So this is just a schematic of the strategy. We have the exhaust fans on the end here. We have recirculating fans placed over the beds. The pressurizing fans are just slightly behind the recirculating fans, so there's enough time for that air coming in to actually get caught into the zone of influence of that recirculating fan and get that air down to the animal level. And then we have the curtain inlet here that could be the side or a combination with the doors themselves, as a way to bring fresh air in as we get to the higher stages of exhaust rates. There's an example of a barn with a fresh air injection strategy, and we're staying, above the 0 degrees Celsius, through this period as the temperature is wavering up and down here in the -7 to even -17 below Celsius. And so it does a great job of maintaining that barn environment. Here's another example that went even further. We were down closer to 20 to 23 below, and still in those at the very short period of time that these barns had a little bit of time where it was below zero. As freezing goes, but it's not enough that it would have to be sustained for a period of time in order to actually freeze up beds or the walkways. So this is a study barn that we did. It's a 1,200 foot long barn, 1150 here, excuse me. And these barns are set up, the parlor is here, holding pen, and this has its both pressurizing system and exhaust. These two barns are fully set up with the partial pressurizing system, the exhaust fans here on the sides on the end, and this is the dry cow barn again that has a negative pressure. So the pressure is pretty well balanced between all of these barns to really reduce short circuiting. These are where the probes are within the barn with the fresh air injection strategy. So we're taking the average temperature across this area, and the probes that we looked at for the study are located just here on this stall before that air is going to start to exit. So the temperature that we're reading is right here before this air that's coming down the alleyway that hasn't been over cows, that's going to start turning out here. So we figured that was the best place to get an example of what this air is like after it's traveled most of the length of that barn. Again, this barn has cows that are producing, around 99 pounds. They got a 30% annual preg rate. We got a 10,040 CFM per cow. We got 36 air changes an hour, and it's a tail-to-tail setup, and they have 55-inch ECV or louvered fans over the inside stall and 52-inch panel fans on the outside row. So this is the barn temperature. During that summer, we had some days where when we had probes in cows and in the environment. So this is the temperature in the barn, and you can see that the recommendation is to be less than 3.6 degrees Fahrenheit of the differential between the inlet and the exhaust, and so we're well within that. We're probably a half a degree Fahrenheit, 1 degree Celsius difference in most cases here of how close we're keeping. And again, we're pulling this air across almost 1,200 feet of barn. And then if we look at the THI over that period, and they have an active soaker system in here too, along with these cows that were virtually in the same, if not better, THI. The blue is the THI in the background here, that we are sometimes at or less than the THI outside after we pull that air across these cows. And part of that is because of the dilution effect of bringing in lower humidity air along with as we move this air down the barn. This is an 8-row barn air injection strategy was a tunnel barn, or it is a tunnel barn, I'm sorry. It used to be a cross vent barn. They had a series of like 120, 25 fans on this wall, and there were baffles bringing the air across this barn. And this was in a very hot, arid climate in the Middle East, and it was not working well. And so the strategy was we take half the fans represented here now are actually exhaust fans turned around that they are pushing fresh air in. There's fresh air being pushed in on the gable ends here, as well as down the side. And then the exhaust fans along the wall here that were existing before, along with some fans relocated down here, that this barn is working much better as a tunnel barn where we are forcing in fresh air, and the air that's being forced in has got high pressure fog on it to cool this air. And then every other one of these louvered fans, as that air is moving down the barn, has high pressure fog on it also. And they're now in the low 40 kilos per day, 9,500 pounds of milk in this strategy now because of the way it's being done. And again, we basically have cut the exhaust capacity in half relative to what it supposedly was before, and we actually have a better barn for it. So this is a picture of how that's working. So the high pressure fog is on the inlet fan blowing into the barn, and then the fans here pushing air down over the cows. And again, with the high pressure fog to cool that, additionally that air. So we're not just pulling in just really hot, dry air. We're pre-chilling that and then also augmenting that with further chilling of that air using the high pressure fog strategy. So, and that's working quite well in that climate. This is a strategy that we implemented and looked at in a dairy in Florida, where in climates where we really don't need to worry about freeze ups, and they're more concerned about humidities and the proper air exchange to create the velocity over the cows. that they've tried the tunnel barn approach, where you're adding more horsepower to the barn, both to bring air down to the cows to create velocity, and then the exhaust fans to create the air exchange. And so it was brought up by Jake Martin and Joe Harner at Kansas State as to, can we use sidewall fans to push fresh air into this building and get the air exchange we need in these real hot, humid climates to create both the air exchange and the velocity on the cows. And so 4 of these fans were set up on the sidewall of a dairy in Florida. And we titrated these vectors coming off these louvered fans, where we first distributed it all the way across. And then slowly we put a angle gauge on here with a measuring device with a laser pointer on it, so we could tell where the louver was supposedly directing the air. And then we kept titrating it back and checking the velocities at the neck rail area, as well as down at 18 inches, to see where can we get the sweet spot here to both get the velocity at the cows first. And then so the vectors that represent how we position these across the cross section of the barn does not reflect really what the air is doing. This was just to give us a way to titrate to find out where is the best set points in order to get the best velocity across that cow lying space. The challenge being that when we push this air across here really fast, and we get over here to the feed lane, which is less than, let's say, 40 feet away, that the mist coming off the soakers when they run is actually pushing the water back onto the feed. So that was the challenge of how do we marry these two conditions together and make it work. And we slowed the fan down then to 50%, and that would allow us to not have this water getting pushed over onto the feed. So if we take a soaker system running at max across 4 pens at every 5 minutes, it will activate that. During that time, the fan would have to slow down to 50% in order to prevent that wetting of the feed. The trade-off is when you slow that fan down, in order to speed it back up again, that takes energy to do that. So that's a trade-off of using more power than to make this work together. And so that needs to be analyzed further. But learning from this, it was discovered that reversing this and eliminate the center feed alley, put the 2 pens together, the barn is no wider because we shifted everything over, that the fans could be put over the headlock area on the outside and feed on the outside, and we'd be able to push that air across that space quite well. And in this setup, depending whether it's a 4 kind of a 2-row head-to-head or a 3-row sort of barn setup, we're pushing in anywhere from 4,000 to 6,000 CFM per cow. And this is designed for a real high humidity climate. This one in particular has several feet of rain a year due to monsoons. And so it's a very humid climate. And if there is nothing, as far as wind going on, these barns are just dead still. And looking at and talking with Dr. Harner, that even in these barns where we have really high humidities, let's say it's 80%, there's still some cooling to be gotten above that if we just turn over the air quick enough. So if we take the outside humidity, it's 80%, there's still some cooling in the psychrometric chart to actually get enough to cause some extra cooling to those cows by increasing the velocity, therefore the volume of air that we're pushing across these cows. So this is something of quite interest in those sort of climates, where both in terms of power reliability, these barns have to be able to operate as a natural vent barn. If they lose power and they don't have enough backup to support that ventilation system, that would be with a tunnel or a cross vent design, that at least it can operate as a natural vent barn. And when it's not and power is there, that they can do a better job of cooling these cows in these climates. So that's a strategy that's being highly looked at for that sort of climate. Again, the idea that we're putting fresh air into this building in an active way, both creating velocity and air exchange at the same time. So this is a video that we took of that setup of how the air is flowing across the beds and as it comes to the stalls. you'll notice as it comes to the headlocks, the air starts rising because it sees that as an obstruction and it wants to start lifting. And so if that was say a 3-row pin without that obstruction, we'd still get air flowing beyond that. And I'll show you some data here later of how this looked with some measurements that we took. So, so with the louvers set the way we set them up, you can see how we're driving the air into the bed area quite well. With the spacing in this case of 20 feet apart. But as you see, as it comes across and starts the air that's backing up behind this, the obstruction of the headlocks and the curb, this air wants to start rising up. And that's what was pushing the soaker water onto the feed. And the idea of flipping this around that the cows will eat on the outside seems a very good solution in that application. And it's something to be learned for other areas that have that challenge. But again, the reducing of the fan speed, becomes a factor of actually looking at the power usage that's gonna, do we still maintain some efficiency with that, with having to slow these fans and repower them back up again on a more aggressive soaking schedule. So this is actually the data that we took a summary of it anyway. So at the outside stall here, the outside head to head, these are the velocities directly in front of the fan. This is meters per second at 48 inch and over here at 18 inches of height. So we've got fairly high here, right directly in front of the fan. It simmers down here just below 3, and we're just below 2 by the time it comes to about 2 feet off the headlock area. Then this is the gap in between. We're right in at 2, 1.5 meters per second in the gap here at 48. But we're looking with that cow lying down, what is she experiencing more at her level? We're looking at 3.5 here, pretty close here on the outside stall area, 3.7 to 3.3 at the inside stall, and we're up here in that 2.6, 2.7, at 18 inches by the time we're out at the headlock. Again, if the headlock wasn't there and we had a wider pack area that's quite common in some areas, we're still going to have some pretty good velocity in that next 15 to 20 feet beyond that to cover the cow area. So we find that to be interesting, and more study has to be put into this to see where this goes. But this is just some early indications of what happens when we try this sort of application. So again, when it comes to integration of these various components into the barn, they have to complement each other. They have to make sense in how they're put together, both in terms of first, what is it doing for the cow, and then is it cost effective in terms of its benefits, and in balance with the negatives, that more fans is more electricity, more initial investment. But in these temperate climate, especially, the number of fans needed for those lower ventilation rates is not a huge amount, and the benefits of preventing freeze up and just issues with in the beds and whatnot, and reducing short circuiting during those times when the exchange rates aren't that aggressive, seems to be quite beneficial, and it's been appreciated by those that have incorporated that strategy. And again, you got to have an automated control that can adjust these systems as it goes through the different variations of the day and the seasons. So the take-home points I'd like you to keep in mind is that we ventilate the cow, not the barn. So we want to make sure that whatever we're doing is focused on her well-being and productivity and welfare. And again, there's various different strategies being tried. And it'll be interesting as to how those shake out as to both what the effects from the cow's point of view, as well as from what the market says as to whether these adoptions are a good idea or not. So a lot of these need some further investigation. Again, for their efficiency and effectiveness. And then, as I said, you have to look at the investment and operational cost versus the benefits to both the animals and the employees in the facilities. So again, I want to thank a few people here that the louvered fan sidewall study was done at North Florida Holsteins. Jake Martin, that's the owner of Dairy Design Engineers, and his assistant, Zoe helped us with this project. Joe DeLong, one of the salespeople with VES-Artex, and then the internal VES-Artex engineering staff that helped with summarizing the data. And so it's greatly appreciated from those folks. And then the fresh air injection study that was done in 2019, that project was done with me along with Dr. Matt Brady of VES-Artex and Spencer Waldner, who was a summer veterinary intern that helped do a lot of the boots on the ground observations during the study period. So great people to work with, and we certainly appreciate their efforts. So we have questions that we can take a look at if there are any.
Yes, we do have one question. And again, if anyone has any questions, please put them in the Q&A chat box below. But the first question, Dr. Wolf, is if the fresh air outside is hot, how does the injected air cool down cows in the barn?
That air in itself would not, unless it's directly involved, like I was showing on the sidewall, where they're even at hot air, if it's below the cow's temperature, if it's equal to the cow's core body temp, we're not gaining much there. Then it's like you're in a brazier oven or convective oven sort of deal. So that doesn't, and that's where in those climates and strategies we need to be looking at adding some cooling through the high pressure fog if we want to directly cool that air, which I showed you an example there in that cross vent barn that was turned into a tunnel facility, and that worked really great that way. So again, the temperature as you would come away from what the cow's core body temp is at 102.2, that if it's cooler than the cow, then the velocity does help to a point. But again, we have to be cooling that cow by either cooling the air or get her an opportunity, which is more commonly done in most climates, is to get able to soak her, and so that we can get that air speed over and evaporate that water off that cow, which will help reduce her core body temp. So they are correct that just blowing hot air on cows is not effective unless we incorporate other strategies with that.
Thank you. We don't have any other questions at this time, so I think we can give it a few more moments just to see if anyone has any. But Dr. Wolf, if you want to go to the next slide.
Sure.
We would just like to invite everyone who is joining us today, whether you are live on Zoom or on Facebook or watching the recording, to please join us for our next few Artex Academy webinars. We have September 3rd, Steve Hamilton of Nationwide is joining us to present on transition planning for farmers and ranchers. And then again on September 17th, we are joined by Dr. Nigel Cook, who's presented with us a few times out of the University of Wisconsin-Madison on designing a robot milking herd to promote efficiency, productivity, health, and well-being. So I don't see any other questions. So I think we are good to wrap up there. I know it's the weekend, so I hope everyone has a really enjoyable weekend. And thank you so much, Dr. Wolf, for presenting to us today. This was a very insightful presentation.
Yep. Well, thank you, and thank you to VES-Artex for allowing me this opportunity. And again, they can reach out to anybody has some further questions that we'd be more than happy to answer if they want further information about some of these concepts and how it may apply to their situation. So again, thanks for the opportunity, and wish you all well.
Wonderful. All right. Thank you.